Imagine this, a telescope so powerful it can peer billions of years into the past, capturing light from the universe's earliest moments. Now, picture that same telescope turning its gaze on two fleeting visitors to our solar system, cosmic wanderers with stories that might rewrite everything we know about our place in the galaxy. In July 2025, the James Webb Space Telescope did just that, uncovering a connection between Comet Swan and the interstellar interloper 3I/A TLAS that no one saw coming. Their chemical fingerprints are so eerily similar, with a 92% overlap in molecular signatures, that astronomers are asking, are these comets fragments of the same ancient catastrophe flung across light years to cross paths in our skies? Or is something even stranger at play? Tonight, we're diving into this cosmic mystery, exploring what these objects tell us about the universe, from their bizarre orbits to their unexpected chemistry, and what they might mean for the search for life itself. Stick with me. This is a story of ice, dust, and secrets from the stars. If you're as fascinated by the cosmos as I am, hit that like button, subscribe, and let's get started. Let's begin with Comet Swan, officially named C/2020 F8, which blazed into view in March 2020. Discovered not by a single observatory, but through a global effort, it was an amateur astronomer, Michael Matiazzo, who first spotted its telltale glow in ultraviolet data from the Solar and Heliospheric Observatory's SWAN instrument. The comet was venting hydrogen, a sign that its water ice was rapidly turning to gas as it hurtled toward the sun. By May 27, 2020, Swan reached its closest point to our star, just 64.6 million kilometers away, dazzling observers in the southern hemisphere with its fleeting brilliance. But its beauty was only part of the story. What made Swan stand out were the numbers behind its path. Its orbit has an eccentricity of 1.15, meaning it's not just looping around the sun like a typical comet. It's on a one-way trip out of the solar system, never to return. This hyperbolic orbit, combined with its steep 111-degree inclination, paints a picture of an object that doesn't belong to our cosmic neighborhood. It's like a guest who crashed the party, stayed for a moment, and then vanished into the night. Swan's trajectory is extreme, even among comets. Most long-period comets, born in the distant Oort cloud, have eccentricities just below 1, meaning they are barely tethered to the sun's gravity. Swan's orbit, however, crosses the threshold into hyperbolic territory, a clear sign it's escaping forever. Its path cuts through the solar system at a sharp angle, diving in from deep space, swinging close to the sun, and then climbing steeply away. NASA's orbital analysts, poring over ultraviolet maps from SOHO, tracked Swan's rapid approach and equally swift departure. By early June 2020, its volatile ices were spent, and it began to fade, leaving behind a trail of data that told a story of cosmic exile. Picture it like a stone skipping across a pond, except this stone never comes back. It's launched into the void, carrying the secrets of its origins with it. Those secrets, locked in its dust and gas, would soon spark a connection no one expected. Now, let's shift to 3I/A TLAS, the interstellar visitor that stunned astronomers in July 2025. Detected by the ATLAS survey team in Chile, this object was moving fast, 58 kilometers per second, or over 130,000 miles per hour. That's more than twice the speed of a typical Oort cloud comet, far too fast to have originated in our solar system. Its trajectory, with a 43-degree inclination to the ecliptic, screamed outsider. This wasn't a gentle arc from the edges of our sun's influence. It was a cosmic bullet slicing through our system on a path that guaranteed it would never linger. The Atlas team's rapid alert allowed the James Webb Space Telescope to lock onto it, capturing spectroscopic data that would turn heads across the astronomical community. This was only the third confirmed interstellar object ever observed, following Oumuamua in 2017 and Borisov in 2019. Each new data point confirmed its alien nature, a hyperbolic excess velocity that ruled out any local origin, and a trajectory that threaded the solar system with almost surgical precision. To grasp the scale of 3I/ATLAAS's journey, imagine a bullet fired from another star system, crossing light years to skim past Jupiter at 0.3 astronomical units and Earth at 1.8 astronomical units. The odds of such a fast, steeply angled object intersecting our solar system are so low that its very presence is a statistical anomaly. Yet, there it was, caught by Atlas's vigilant sky patrols, racing past our sun on a one-way ticket to the stars. Its speed and path alone were enough to make headlines, but it was the James Webb's chemical analysis that turned this discovery into a game changer. Unlike typical comets, 3I/ATLAS wasn't dominated by water vapor. Instead, its coma, a cloud of gas and dust surrounding its nucleus, was bursting with carbon dioxide at levels 16 times higher than any solar system comet observed at a similar distance. This wasn't just a comet, it was a chemical oddity, challenging everything we thought we knew about how comets form. Let's pause for a moment to appreciate what this means. Comets are like time capsules, preserving the chemistry of their birthplaces. Most form beyond the water ice line in a star's protoplanetary disk, where temperatures are low enough for water to freeze. But 3I/ATLAS's carbon dioxide dominance suggests it formed much farther out, near the CO2 ice line at about 80 Kelvin or minus 193 degrees Celsius. This is a region so cold that only the most volatile ices, like carbon dioxide, can condense into solid form. The James Webb's spectrograph measured a CO2 column density of 7.6, with a margin of error of just 0.3, a value so extreme it sent researchers scrambling to redraw their models of comet formation. This wasn't a fluke. Multiple calibration runs confirmed the data. 3I/ATLAS is venting O2 at a rate that suggests its parent star system was either extraordinarily rich in carbon dioxide or exposed to unique conditions that favored this molecule over water. It's a clue that this comet didn't grow up in a typical stellar nursery. It came from somewhere far stranger. Now, let's bring Swan back into the picture. In April 2020, its own moment of glory came when SOHO's ultraviolet maps captured a massive hydrogen flare, signaling a surge of water ice vaporizing into gas. But what really caught astronomers' attention was its dust production, peaking at 30,000 kilograms per second, enough to fill an Olympic swimming pool every hour. Unlike most comets, which are gas-heavy, Swan was a dust factory, scattering sunlight with fine particles that outshone its gas emissions. This high dust-to-gas ratio was the opposite of 3I/ATLAS's CO2-dominated profile. Yet, when researchers overlaid the spectral data from both objects, something astonishing emerged: a 92% match in their molecular bands, with a statistical p-value below 0.01. In plain terms, this means the odds of this similarity being random are less than 1 in 100. From carbon dioxide peaks to faint traces of carbon monoxide and organic molecules, their chemical fingerprints were almost identical, like 2 pages torn from the same ancient book. This overlap isn't just a curiosity, it's a cosmic puzzle. How could 2 objects, one a hyperbolic solar system comet and the other an interstellar visitor, share such a close chemical signature? To answer this, researchers turned to impact models, imagining a massive comet nucleus, perhaps 5 kilometers across, shattered in a distant star system. A collision at tens of kilometers per second could scatter fragments across the galaxy, each carrying the same chemical makeup, but launched on wildly different paths. Some might escape their star's gravity entirely, becoming interstellar wanderers like 3I/ATLAS. Others might linger in their home system, nudged toward our sun millions of years later, like Swan. The velocity dispersion from such an event, just a few meters per second difference at the moment of impact, could explain why one fragment arrived in 2020 and another in 2025, their paths converging in our solar system by sheer cosmic chance. But there's another layer to this mystery: the nickel isotope anomaly. When the James Webb dissected 3I/ATLAS's light, it found a ratio of nickel isotopes that doesn't match anything in our solar system's comets. Swan 2 showed faint traces of a similar isotopic quirk. Nickel atoms, forged in the hearts of ancient stars, act like a cosmic barcode, hinting at a birthplace around a star with a different nuclear history. This isn't just a random quirk. It's a clue that both comets may have formed in a system with a unique chemical recipe, perhaps one shaped by a supernova or a massive stellar collision. The odds of 2 unrelated comets sharing this rare isotopic signature are so low that researchers are seriously considering the possibility that Swan and 3I/ATLAS are fragments of the same parent body, scattered across light years but reunited in our skies. Let's take a step back and consider the bigger picture. Only 3 interstellar objects have ever been confirmed: Oumuamua, Borisov, and now 3I/ATLAS. The Minor Planet Center and NASA's Center for Near-Earth Object Studies estimate that we should see 1 or 2 such visitors per century, based on the sparse population of interstellar debris. Yet, within 5 years, we've caught 2. Swan, with its borderline interstellar traits, and 3I/ATLAS, a clear outsider. The chance of them sharing a 92% spectral match and arriving so close together in time is so remote that Harvard's Avi Loeb has called it the cosmic equivalent of lightning striking twice. This isn't just about statistics, it's about what these objects might be telling us. Are they debris from a single cataclysmic event, like a planetary collision in another star system? Or do they hint at a broader population of interstellar objects we've only begun to detect? The orbital paths of these comets add another twist. When analysts map 3I/ATLAS's trajectory, they noticed it resembles the carefully planned flybys of spacecraft like Voyager or New Horizons. It skims Jupiter and Earth at just the right distances, 0.3 astronomical units and 1.8 astronomical units, respectively, to maximize speed without colliding. Swan's path, while less precise, also avoids planetary entanglements, climbing steeply out of the solar system. These optimal transfer arcs are so efficient They almost mimic human-engineered trajectories. There's no evidence of artificial propulsion, no non-gravitational acceleration or jetting to suggest anything unnatural. But the precision is uncanny. Nature, given billions of years, can produce such coincidences. But the similarity to mission-planned orbits has sparked whispers of speculation, even among cautious researchers. Then there's the dust plume anomaly in 3I/ATLAS. Typically, a comet's dust jets are pushed directly away from the sun by solar radiation. But Webb's polarimetric studies showed 3I/ATLAS's strongest dust emission veering at a sharp angle, defying the expected direction. This isn't a simple quirk of rotation or surface fractures. It's as if the dust is being steered by some internal mechanism. Most astronomers lean toward natural explanations, like uneven heating or buried ice pockets. But a few, like Avi Loeb, argue it's worth considering what if. Could this be a sign of exotic physics, or, in the most speculative view, a techno-signature? No one's claiming 3I/ATLAS is an alien probe, but the anomaly has opened the door to questions that push the boundaries of comet science. Let's address a common misconception here. Some online chatter has suggested that interstellar comets, like 3I/ATLAS, could be artificial objects, spacecraft from distant civilizations. While it's tempting to imagine, the data points firmly to natural origins. The nickel isotopes, CO2 dominance, and orbital dynamics all align with known astrophysical processes: star formation, ice line chemistry, and gravitational scattering. The alien hypothesis, while intriguing, lacks any concrete evidence, and the scientific community remains focused on natural explanations. That said, these anomalies remind us how much we still have to learn about the universe. If you're loving this dive into cosmic mysteries, drop a comment below with your thoughts. Do you think these comets are connected? Or is this just a wild coincidence? The implications of Swan and 3I/ATLAS extend beyond their origins. Their chemistry, particularly the presence of complex organics in 3I/ATLAS's coma, has astrobiologists buzzing. These molecules, potential building blocks of life, could have survived a journey across interstellar space, preserved in ice since before our sun was born. If these comets carry prebiotic compounds like amino acids or sugars, they might hold clues to how life's raw ingredients spread across the galaxy. Sample return missions like NASA's Stardust or OSIRIS-REx have already brought back comet dust from our solar system. Now, engineers are eyeing 2035 as the earliest window for a mission to intercept a future interstellar visitor. The challenge is immense. A probe would need to withstand impacts at tens of kilometers per second and return samples shielded from deep space radiation. But even a few grams of material could revolutionize our understanding of planetary chemistry and maybe biology. Human exploration isn't off the table either. NASA's Artemis program and private companies are sketching out concepts for crewed missions to comets, where astronauts could collect samples in real time. Imagine a team landing on an interstellar object, drilling into its icy core to uncover molecules from another star system. It's a long shot, but the technology is closer than you might think. Meanwhile, clean labs in Pasadena and Paris are being prepped to analyze any future samples for signs of life's precursors. Every molecule recovered would be a data point in the search for our cosmic origins. Did these organics form in the cold voids between stars, or were they forged in the chaos of a newborn system? the answers could redefine how we see life's place in the universe. As we wrap up, let's reflect on what Swan and 3I/ATLAS tell us. Their 92% chemical match, hyperbolic orbits, and rare isotopic signatures suggest a shared history, perhaps as fragments of a shattered parent body from a distant star system. Their paths through our solar system, precise and fleeting, remind us that we're not an isolated island, but a crossroads for cosmic travelers. The James Webb's data, carbon dioxide spikes, nickel anomalies, and organic traces has opened a window into a universe far richer and stranger than we imagined. These comets aren't just ice and dust, they're messengers, carrying stories of ancient cataclysms and the chemistry of distant worlds. As mission planners gear up for future flybys and sample returns, we're on the cusp of answers that could change how we see our place in the cosmos. So, what's next? The hunt for interstellar visitors continues, with telescopes like ATLAS and Webb scanning the skies for the next clue. Each new discovery brings us closer to understanding the debris that drifts between stars and maybe the origins of life itself. If this journey into the unknown has sparked your curiosity, hit that like button, subscribe, and share your thoughts in the comments below. Are Swan and 3I/ATLAS siblings from a lost world, or is their connection a cosmic fluke? Let me know what you think, and let's keep exploring the universe together.